clear because the covariance is linear. So basically, if you covariance of some scalar multiple of a random variable is that scalar multiple multiplied with this the covariance of the two variables, and you can, it is also distributive. So it's basically a linear function. Covariance is a linear function on the set of random. So what I wanted to say, yeah. So I gave you an exercise. If xt show that, let me write here like this, show that if xt, oh, by the way, yeah, we always now assume that the time series is stationary. Okay. So if xt is moving average process, I can write something like this. It's like equivalent to a moving average process of order r. Then the covariance, the gamma k is equal to 0 for k bigger than r. Okay? And this is very simple because gamma k is the covariance of xt and xt plus k. So if k is bigger than r, then you know that xt's are IIDs, so the covariance of those xt's will be 0, so you will be left with nothing. So unless there is an overlap in the lags, you always get autocovariance as 0. I also defined autocorrelation to be rho k. Again, it depends only on lag for a stationary time series. So rho k was defined to be this gamma k divided by gamma 0, and gamma 0 is the variance of xt, which is constant because of the stationarity. So gamma 0 is the variance of xt. Okay. So is this clear? So far what we have done is clear?
Yes, sir.
Okay. So now the question is, suppose we are given a time series. Suppose xt is given. So by xt given means we have a sequence of some, let's say, real numbers or something. Some time series data is given. How to estimate the covariance? No, not, I don't want to do this one first. What I want to do is, suppose we have two data sets are given. Okay, suppose, how do I say this? Suppose, let's say n pairs of observations, some observations, we don't know what. Let's say x1, y1, x2, y2, x3, y3, and so on are given. So I can assume, I can assume that they are drawn from some two random variables, some n observations drawn from two random variables x and y. So can be considered as n observations drawn from two variables x and y. So um, now we don't know the random variables, we don't know nothing, but the covariance. So first of all, mean. How do you define a mean of such observations? Anyone? So I mean,
For
you are given, let's say, a set of points, not in R2, but x1, x2, x3, xn. How do you estimate the mean of this set?
we take the mean of first in one dimension, we like
Yes.
for two dimension we can take mean of one dimension in both the dimensions. Like for we'll take the mean of all the x1s, x2, x3, x1, x summation xn upon n,
Right. Right.
and then we'll take summation yn upon n, then
Okay.
we'll take the
So the mean of x will be let's call it x bar. Okay. So this will be, you are saying, summation n equals 1 to I equals 1 to n xi divided by n, right? This is what you are saying. And the mean of y is y bar equals summation I equals 1 to n yi divided by n. This is how we estimate. This is the estimated mean, or a sample mean is what we call it. Sample mean, right? Now, how do we measure, how do we estimate the covariance is what I am trying to ask. So covariance of this, what is called the sample covariance. Sample covariance of x and y. This is measured as gamma equals summation I equals 1 to n xi minus x bar times yi minus y bar divided by capital N. This is how we find the sample covariance of two random variables. Now, how to estimate autocovariance of a time series xt. Now, in this case, we just have like a sequence of points, right? X1, x2, x3, x4, and so on. So, how do we then estimate the covariance? What is that function a cov v that you must have seen in this library stats models? You have seen. Have you done that? Tried that? So, what is
Yes, sir.
that? So this is what it does. So for time series xt, well, given n observations, let's say x1 up to xn on xt, a realization. So we know how to find the variance, like covariance. We know how to find the covariance. It's basically um, just the variance of this. So we know how to estimate that. But for lag 1, what is gamma 1, for example? So what we do is, so what is the estimated value of gamma 1? Okay. So what we do is we form pairs x1, x2, x2, x3, x3, x4, and so on, x n minus 1 comma xn. This is what we take these pairs. So okay, and we estimate gamma 1 to be the covariance of xt and xt plus 1. So in this case, it will be 1 over. Now we only have how many observations we have? These are only n of them, right? N minus 1 of them. So I use the formula that we saw in the last slide. So it was 1 over n minus 1 summation t equals 1 to n minus 1, then xt minus x bar. We know how this x bar is the mean, which is constant because we assume the time series is stationary, and xt plus 1 minus x bar. Okay, this is how we estimate. So this is what is called the sample autocore variance, and this is what the function ACOV calculates when you give it in Python. So, and similarly, the sample autocorrelation gamma rho is denoted by rho. Similarly, rho of k. So this is gamma 1, and let me write the general formula for gamma k. So gamma k will be 1 over capital N minus k summation t equals 1 to n minus k xt minus x bar xt plus k minus x. Okay? And this rho is just we divide by the variance, so that's what we will get this autocorrelation function. So this will be correlation of xt comma xt plus k, and this will turn out to be summation I equals 1 to n minus k xt minus x bar xt plus k minus t here divided by summation I equals, I should write a little smaller here. So summation I equals 1 to n xt minus x bar squared. So this is what we get as autocorrelation of a stationary time series. This is how it is estimated. Okay. So now, so if a time series is non-stationary, then to analyze that time series, there are some ways to make it stationary. So let's see, like one simple example. If a time series is not, what do you do then? Right? So let me first ask you a simple question. So suppose the time series is not stationary. The question is, what can you say about the autocovariance in this case? So any idea? What? So suppose you are given a set of data and you estimate the autocovariance and autocorrelation functions, and suppose that time series is not stationary. So what can you, how would autocovariance turn out, or autocorrelation turn out?
Sir, in this case, since we don't have a constant mean,
Yeah.
so each term will have a separate. Each term can have can have a separate mean involved into it.
Yes. And
And since again the gamma, the covariance of xt and xt plus k is not constant.
yes.
Like apart from k, other factors are also involved into it.
Mm.
So again, the product that we will have
Yeah.
will again give have one more factor to be uh,
Mm.
one more factor of irregularity.
Right. Yeah, basically, the I mean, what you will get is some non-zero quantity for every gamma k, right? This is what will happen for sure. So, so what I want you to do is, so, okay, we will talk about this a little later, but yeah. So basically, what you expect is the covariance will not be zero for any k. This is what will happen. And so, what I wanted to say was, you basically will have no meaningful idea about the time series, right? This is what I was about to say. Anyway, so let's move on a little and do something different. So let's talk a little bit more about stationarity. So we know the definition of stationarity, and you recall our random walk. Okay. So what was random walk? Does anyone remember?
Xt equal to xt minus 1
Yeah, xt minus 1
plus a
plus
random
some
variable
noise.
noise, maybe. Yeah.
Yeah, some noise. So this is, and this was, we assume that they are normally distributed, mu, like mu with mean mu and sigma. So now the question is, what is the autocovariance of this one, right? So first of all, is xt stationary? If I define, if there is a, suppose a time series follows this kind of relation, then the question is this time series stationary? So let's see what happens then. So without loss of generality, assume x0 is 0. Okay. So now if x0 is 0, then x1 will be epsilon 1, right? And x2 will be then epsilon 1 plus epsilon 2. We just use that definition, and so on. So then x t will be summation I equals 1 to t epsilon I, right? This is what will happen. And if I calculate the variance, so first of all, what is the mean of xt? It will be the mean of summation I equals 1 to t epsilon I, right? And what will it be?
This summation over t.
Right, so it will be mu1. So no, now we assumed that each of these epsilon i's are normally distributed with mean mu. So it will be, uh, there's some discrepancy with the notation, but I assume you understand. Um, it will be t times mu, because there are t number of epsilon i's. So when you take the sum of the means, it will be t times mu. Is that clear? The mean of xt.
Here the mu is the
Yeah, epsilon i's were normally distributed with mean mu and sigma square. So each xi has mean mu. So if each xi has mean mu, then mean of xt will be t times mu, right? Because expectation or mean is linear. So this
yeah.
happens, right?
Yeah, but sir, won't it, okay, the summation now it's just all the oh, already it's some mean. Okay. No, sir, sorry.
Is that clear for others? Are you with me or not? Okay. And similarly, the covariance of xt. What will be the covariance of xt? Or variance of xt, I should rather say. I'm sorry. The variance of xt. But this will be t times sigma square, because variance is also linear, right? A linear function. So so if you take the variance of xt, the variances of sigma i's will sum up. So you will get t sigma square. And you see that in case of random walks, so this implies that random walks are never stationary. Unless mu and sigma square are both 0, right? So then the time series will have no meaning unless mu and sigma square both are 0. So random walks are not stationary. Okay. Now, what I want you to do is to uh, exercise is just plot the autocovariance of a random walk. So you simulate a random walk and then just forget about anything, forget it's not stationary, just plot the autocovariance and see what happens. And you will see that the autocovariance will never be 0. So it will give, basically the autocovariance gives no meaningful information about the time series. On the other hand, we know that if a time series is a moving average process of order r, then only this row 0, row 1, row 2 up to row k will be non-zero, rest all will be 0. So now imagine you take some data, you plot the autocovariance of the data, and you find that only first few autocovariances are non-zero. So what does this mean? This means that our time series uh, can be modeled as a moving average process of order r. So it will be, so you will have information about the autocovariance. All you have to do is to find the coefficients, these ai's and all, and so you will have to find the mean of the epsilon t's and variance of epsilon t's. And once you are done, you basically have modeled the data in a moving average process of time series. So this is usually what we do. We will see some examples a little later, but um, well, for now, because we need some more definitions before we can see examples. So let's move ahead a little and now consider the following situation. So consider the following MA process, moving average process of order 1. The first is, let's say, xt, which is zt plus some theta zt minus 1. Okay. And there's another one, yt, which is zt plus 1 divided by theta zt minus 1. Okay. And suppose that they are stationary moving averages process of order 1. So can someone calculate quickly? Suppose also that, I don't know what to write here. Yeah. Suppose ZTs are normally distributed with mean 0 and variance sigma square. Okay. This is what we have. Now, can someone calculate quickly the row of, let me write row x of k. So meaning the autocorrelation of this k, of xt. Anyone?
Sir,
All
is
you,
this stationary?
yeah, it's stationary, yes.
So for k greater than 1, it will be 0.
Right. So the only one, only two quantities will be non-zero, right? For k equals 0
And 1, yeah.
and 1. So, and for k equals 1, I know it's um, k equals 0, it will be some variance of, it will be, what will be the variance of xt? Yeah, so I want you to calculate this. So let's say I want you to calculate gamma x of 1. What will it be? Okay, I'll give you the answer and I'll leave it as an exercise. It's not very difficult. You just have to expand the formula. So it's basically uh, this correlation of xt and xt minus 1. Xt minus 1 or xt plus 1, it doesn't matter, right? So, and you will see that you will get theta divided by sigma square times 1 plus theta. Okay, you will get this quantity here. And calculate also rho y of 1. So this will be correlation of yt and yt minus 1. And you will see that the only difference here is basically, this will be theta squared here. Theta divided by sigma square times 1 plus theta square. And this will be 1 over theta divided by sigma square into 1 plus 1 over theta square. And you will see that this will also be theta divided by sigma square into 1 plus theta square. Okay. And you see that although these two time series, xt and yt, are very different from each other, the correlation coefficients are both the same. So, is it clear? You have to do the calculations. You have to find this rho 1 and rho 2, rho 1 of x and rho 1 of y. So correlation coefficients of xt and yt are both the same. Okay. So what does this mean? Well, this means that autocorrelation function does not determine a moving average process uniquely, right? It's possible that there are two very different moving average processes, but their correlation coefficients are the same. And here is one example. Okay, so this doesn't give the the moving average process is not determined by the correlation, is what I'm trying to say. Okay, so you need to find also this sigma square and mu and so on. If you want to find, if you really want to model some time series into moving average process, you need to, correlation is okay, but you also have to find the sigma square, mu and so on. Okay, but there is one difference between these two time series. Okay, so what is that difference? So what we can do is this. So xt is zt plus theta zt minus 1, right? And so zt will be xt minus theta of zt minus 1. Okay, and now I can do the same thing here. I can replace this zt minus 1 as xt minus 1 minus theta of zt minus 2, right? I can do that. So xt minus theta of xt minus 1 minus theta of zt minus 2. And now again I can do the same thing here. So this I will get as xt minus theta xt minus 1 plus theta into xt minus 2 minus theta into zt minus 3. Okay, and so on. I can keep on going. So eventually, sorry,
this one is theta square. Actually, second
theta
one.
is squared. Yes. Where theta is squared?
Theta square xt minus 2 minus theta. Outside
Here.
bracket.
Yes. Yes. Yeah, you are right. Yes. So I can continue in this way, and I will have zt equals summation I equals 0 to infinity minus theta to the power I x t minus I, right? And for the other one, yt, the other time series, this one here, for this one I will get zt equals summation I equals 0 to infinity 1 over theta, 1 over minus theta to the power I yt minus I, right? So what we are doing, is it valid? Do you think it's valid? Can we do such something like that? When do you think we can do something like that? When do you think we can write zt as this infinite sum?
When theta is non-zero, I guess.
No, that's not a good answer. I mean, you have studied all this calculus and differential equations and all.
When it is bounded.
When it is not bounded, when it is convergent. Okay. So we can do this. So the question is, can we do this? Can we write zt as an infinite sum? Well, the answer is yes, if the sum converges. Okay, but converges in what sense? So it converges in what is called a mean square convergence. Okay, so we'll talk about this mean square convergence some time later, but let me just write down the conclusion. So zt equals summation minus theta to the power I xt minus I is convergent if mod of theta is less than 1. So you have to really use the ideas from measure theory and calculus to really prove this thing. So convergent in mean square. But there is a way to cheat this. So I mean, we can actually cheat this and say we can see that theta must be less than mod of theta must be less than 1 for this to be convergent. And the cheating is this. Here is what we can do. So given beta, given let's say yt, we put b of yt to be yt minus 1. Okay, let's put this. And if we do that, so with this notation, yt will be zt plus theta bzt, right? Now I am confusing you actually. I shouldn't write. What I'm trying to say is given, let's say I've used z also. So, given, let's say kt, what we do is we put beta of kt to be equal to kt minus 1. Okay, so now with this notation, this is just a notation, our yt or xt will become zt plus theta bzt, right? With this notation, look, it was defined like this here. So I will write zt as b of zt minus 1 as b of zt. So this will be same as yt equals zt into 1 plus theta b. Okay, and then zt will be equal to 1 over 1 plus theta b times xt, right? This will happen. And now I know this thing can be written as a geometric series, like 1 minus theta b plus theta square b squared minus theta cubed b cubed and so on, xt. So this you will eventually get summation I equals 1 to 0 to infinity minus 1 to the power minus theta to the power ix t minus I. Okay, but when can we write this kind of geometric series as 1 over 1 plus? So when can I write 1 minus r plus r square minus r cubed plus so on as 1 over 1 plus r? That's when mod r is less than 1. So for a second, if you forget b, you have mod this from here to here. I can do this if mod theta is less than 1. So this is like, yeah, it's not rigorous mathematical argument, but you can see what's going on, right? This is what we can do. Okay, so right, so if zt can be written as summation I equals 0 to infinity minus theta to the power I xt minus 1 I, we say xt is invertible. Okay, and if theta is less than 1. So this is, so the examples that we took here, these two examples, although the correlation coefficients are both the same for xt and zt,
Excuse me,
yeah,
sir.
yes,
Sir, here you are taking I from 0 to infinity, right?
0 to infinity, yes,
But sir, I should always be like goes to 0 to t.
right. What, I should go from 0 to t?
Yes, sir. For zt,
No,
it should go from 0 to t.
no, we, indices doesn't matter. You can also write the indices as minus. It doesn't matter. You understand what I'm saying? So instead of starting your indices from, let's say 0 and going up, you can also go down 0, -1, -2, and so on. This is what indices don't matter really. It's just a representation.
Okay, sir.
Okay. So yeah, so there's the difference. We have found a difference between these two series. This one, if mod theta is less than 1, then xt is invertible, but yt is not invertible. Okay, this is something that we will use later on, the invertible. Okay, so with this I will stop and we'll meet tomorrow. If you have any questions, let me know. And of course,